Okay, just want to say that we're gonna do this chapter on the mole. Okay, we're gonna do this chapter on the mole. So let's start with the first worksheet. Okay, that we're gonna go through. For this session, I hope we can at least go through 2 worksheets today. I think as a start, okay, let me use the highlighter to just show you what we're gonna go through. Okay, first things first. For today, we are in terms of the mole, we're gonna find out what exactly this chapter is about. In addition, okay, we're gonna be doing all of the things over here. All right, we will do it step by step, so it won't be too difficult. So this worksheet is very broken down such that you just need to tackle one part of the mole each time. So I say again, in this worksheet, what I tried to do is to break down one part of the chapter one step at a time. Okay, so it shouldn't be too difficult, but the difficulty will come when we try to put all the different things together lah. Okay, so segment by segment, make sure you're able to comprehend, you're able to understand. Okay, so I repeat again, segment by segment, make sure that you're able to understand and comprehend. Okay, only when you have that full understanding of each segment, then it will definitely be a lot easier when we try to put everything together. Okay, so let's start. As I mentioned before, okay, all of these worksheets are actually based on your textbook. So you can actually refer to your textbook to try to do these worksheets as well. Okay, so let's start. Okay, so why is this chapter important? Okay, just take note, the actual mass of a carbon atom, okay, the actual mass of a carbon atom, you want to find the mass of an atom, okay, it's actually very, very small. It's actually 2 times 10 to the power of negative 23 grams. Okay, it's actually very, very small number. Can you imagine you need to use this kind of numbers to make all your calculations? It's a bit ridiculous. Okay, so what scientists try to do is, instead of using such numbers to calculate the mass of different atoms and stuff, okay, actually what they try to do is they use this idea of relative atomic mass, which all of you have always been using. Another word for relative atomic mass that many of you actually started using in the chapter of atomic structure is actually your nucleon number. Okay, let me write nicer here. So this idea of relative atomic mass, okay, actually is nothing too new. You actually know this as your nucleon number. Okay, so the nucleon number is actually the relative atomic mass. It tells you how heavy the atom is. Okay, so instead of using such ridiculous 2 times 10 to the power of negative 23 grams kind of number, okay, we use something more simplified, which we call the relative mass. So where can you find the relative mass? Okay, so instead of going to definition first, so I'm just going to show it to you. So if you go to your periodic table, okay, you can see here, there's always this idea of the legend over here. There's this part that says the relative atomic mass. So all of the bigger number, so let's say for lithium is a 37, okay, 37. 7 is the relative atomic mass. It tells you how heavy the lithium atom is relative to something. So question is relative to what? Okay, why do they call it the relative atomic mass? So this is where we go into the definition now. Okay, define what relative atomic mass is. Okay, so the relative atomic mass of an atom, okay, the relative atomic mass is actually the average. Okay, it's actually an average mass of one atom of the element. Okay, it's the average mass of one atom of the element. Okay, so it's the average mass of one atom of the element. Now, because it's relative, so it's compared to something. So the question is, what is it compared to? Okay, it's actually compared to 1/12 of the mass of a carbon 12 atom. Okay, it's actually compared to 1/12 of the mass of a carbon 12 atom. So that is the definition of relative atomic mass. So the question a lot of people always ask is, why is it 1/12 of the mass of a carbon 12 atom? So let's assume that actually, okay, your carbon 12 weighs 12 units. Because carbon 12, right? Let's take it as carbon 12 weighs 12 units. So 1/12 of the mass, 1/12 of 12 units is actually equals to 1 unit. Okay, sorry, let me write properly. 1/12 of 12 units actually equals to 1 unit. Okay, that's why they use 1/12 of the mass of a carbon-12. So assuming that carbon-12 actually is consisting of 12 units of mass, okay, 12 units. So 1/12 of it is 1 unit. So it makes it very easy lah, okay, to compare. So do take note, because relative atomic mass is a comparison, it's a ratio. So therefore, whenever we talk about relative atomic mass, it actually has no units. Okay, so relative atomic mass actually has no units. Now, of course, this is just definition. Okay, this is a definition. How exactly to use it? What does it exactly mean? Okay, so I'm going to show you one implication here. We're going to show you one implication here. So not all relative atomic mass are whole number. An example is the element chlorine. So if you go to your periodic table, you realize, sure, my chlorine is 35.5. Last time when I tried to use 35.5 to calculate my number of neutrons, okay, it's kind of weird. How can I have half a neutron? So why is it 35.5? So this is where we will start to come in to explain why is it 35.5. So let me explain to you, okay, why are some relative atomic mass not whole numbers? So let's give you an example. So instead of writing the answer, why are they not whole numbers, I'm going to zoom in a little bit on the left-hand side so I got more space to write. Okay, so let me explain to you using the example of chlorine. So now chlorine actually got two isotopes, two main isotopes. Okay, so I say again, chlorine actually has two main isotopes. There's chlorine 1735. There's actually chlorine 1737. So this number 37 and 35, they are your nucleon number. They're also your relative atomic mass. Now, the interesting thing is this. When they take a sort of like a sample, they realize that chlorine 35 actually consists of 75% of all the chlorine in the world. So if I will take all the chlorine atom in the world, right, 75% of them will be chlorine 35. 25% is actually chlorine 37. Okay, so that's why what they do is they check out, okay, how many of each isotopes do I have? So for chlorine 35 is 75% of all chlorines are chlorine 35. 25% of all chlorines are chlorine 37. So the question is this, okay, now I know it's 75%, 25%. How exactly did you get this relative atomic mass of 35.5? So it's actually based on a calculation. So to find the relative atomic mass, you actually use the percentages. So what you're going to do is, you're going to assume, okay, not going to assume, you're going to use this idea of there's 75%, so 75 over 100 of chlorine 35. So you take 75 over 100 times 35. Okay, you're going to add 25% of chlorine 37. Okay, so I say again, actually you take 75% multiplied by the mass of the chlorine 35, which is 35. Okay, next thing, you're going to let me do something first. Okay, I realize I need to let people in, but I can't let people in. Oh no, this is bad. Anyone using computer here? Can anyone help me to become co-host to let people in? Anybody? Anybody? Who can help me to let people in? My computer is not performing that well. No one want to volunteer. Okay, I see Tyler. Okay, Tyler, you help me. Okay, so I'm going to make you co-host. Please don't go and do rubbish with the co-host status. Okay, so anyway, let's carry on. So if you were to take your calculator and press the numbers and crunch the numbers, you're going to get 35. Okay, sorry. Okay, so you take the numbers and you crunch it, you're going to get 35.5. Okay, so you're going to get 35.5 in terms of your value here. So the relative atomic mass is actually calculated based on the percentages of each of the atoms. So then, okay, now you understand, okay, this is how you calculate this, how it is 35.5. So the question now becomes, okay, now I know how to calculate, but how exactly do you explain? I understand the idea, okay, of using math to try to explain why is it 35.5, why they're not whole numbers. But the question is how to explain, okay? Well, how to explain. So the way to explain is this, okay? First thing you're gonna say is actually that your elements, you're gonna say that your elements, okay, exist. Wow, my thing not smooth already. Let me try to adjust a bit. Okay, so your elements exist, okay, as a mixture of isotopes. Okay, I realize this handwriting is not working. Let me try to restart my ClassKick. I think it's the browser that is giving me issues here. Okay, sorry everybody. Let me pause the recording first so that I won't have any. Okay, so let's carry on. Okay, so actually your elements exist as a mixture of isotopes. Like just like chlorine 35, chlorine 37 is a mixture of isotopes, two different isotopes, right? Then the relative, wrong color, the relative atomic mass, okay, the relative atomic mass, okay, is actually calculated based on the relative percentages of the isotope. So this is actually the explanation. Okay, what we have done just now, okay, I say again, what we have done just now was to do the calculation. By doing the calculation, it's actually sort of like the explanation. Why? Because we say, first thing, elements exist as a mixture of isotopes. So chlorine exists as a mixture of isotopes, chlorine 35, chlorine 37. Then why is it that they are not whole numbers? It's because the relative atomic mass is calculated based on the relative percentages of isotopes. Like what I've done here, we know that chlorine 35 is 75%, chlorine 37 is 25%. Therefore, when I calculate the relative to atomic mass, it gives me a 35.5. So that's actually how you go about answering, okay, both mathematically and also in words, okay, regarding why the relative atomic mass, the AR, are not whole numbers. So some of you may say, sure, AR, why is it AR? Think of the R as a relative, think of A as the atomic mass. So you're going to see AR, relative because of the R, atomic mass, that's why capital A over here. So that's actually how you go about writing relative atomic mass in terms of symbol. Okay, so right now, okay, we got actually I got two questions, if I'm not wrong. There's one question on bromine. If you go next page, there's one question on oxygen. So I just want everybody, I'm going to pause the recording. I just want to give everybody some time, okay, to just try to do the calculation, okay, because no point just me doing every single question, right? I want you all to go and try doing the question. So maybe take about the next 3 minutes. So okay, yeah, take the next 3 minutes. So now is 10:45. I give you until 10:48 to go about doing the 2A and 2B. Then we'll go through it. Okay, so have your calculators, you can use your handphones whatsoever. Okay, so I'm gonna pause the recording now. Okay, please go and do in the next 3 minutes. Let's go. Let's resume. Okay, so most of you would have done this question already. I hope you don't find it too difficult. But what's important is that you actually write down the statements. Okay, I think presentation is important, and I need you all to make sure that you write your presentation carefully. So in this case here, how to exactly do the presentation? Please don't just write numbers there and stuff. Okay, I think in chem, statements are important, especially for this particular chapter. Okay, some people are asking me, should I write 3SF? Should I put 2DP? In chem, put it very simply, all your final answer generally put to 3SF. Okay, final answer generally put to 3SF. So let's do this. So what we're going to do is we're going to write, so relative atomic mass, okay, of bromine. Okay, so some of you never write bromine, just relative because there's only one element there, bromine, right? So what I'm going to do is, I know there's 50.69% of bromine 79. So 50.69 over 100 multiplied by 79. I'm going to add this with 49%, 49.31% of bromine 81. Okay, so those of you who have done your math, you realize the number comes to this 79.9862. So as I mentioned, leave your final answer to 3SF. So I'm going to round it up to actually 80.0. So I'm going to write here 3SF. And you realize this number actually tallies with what you have in your periodic table. So bromine, relative atomic mass is 80. Okay, relative atomic mass is 80. Now, I want to show you the idea of why are we doing this relative atomic mass. So you say, all of them whole number, only chlorine is the weird one. So because your periodic table is actually simplified for you, if I were to include all the elements isotopes and to calculate the relative atomic mass, actually all of them will look kind of weird. So for example, bromine, okay, what I gave you was only 2 of the isotopes. There are actually some of the others. So if you calculate, it will actually give you a number of 79.904. So if you look at that kind of number, you realize, 79.904. Well, how many other isotopes there are? So actually, if you go to this P table, you can actually click on isotopes. You can actually see all the number of isotopes that, okay, so there's actually tons of isotopes that bromine has. So you look at the thing here, can you see bromine 67, 68, blah, 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 until tons, okay? There's a lot of them. So what we are teaching you here is only the basics, okay? But to appreciate it, to really see how it's being applied, actually is at a higher level. Okay, so you go to properties, you realize this, all the mass, okay, all of the masses you can see here, even for carbon, it's not carbon 12, it's the relative atomic mass is 12.011. Even for hydrogen, you realize it's 1.008. So all of this actually comes into play when we are calculating the relative atomic mass and stuff like this. Okay, so let's go back to the question. So this is for bromine. Let's go on to the next page. So next one we have is oxygen. So once again, I'm going to write the answer here. So relative atomic mass of oxygen. Okay, we are looking at the oxygen atom. So in this case here, what I'm going to do is I'm going to take 99.762% of oxygen 16. Okay, I'm going to add this with 0.038% of oxygen 17. And I'm going to add 0.200 over 100. Okay, so 0.2% of oxygen 18. Okay, let me press my calculator. So I'm also pressing my calculator. I haven't done it yet. Okay, hopefully I'll get the same answer as all of you because I didn't press any silly calculation error. Okay, 0.0. Oh no, shut up. Sorry, Oh no. Okay, anyway, sorry, I realized I pressed wrongly. Okay, 9.4. You can see I have very long press calculator. I ask you press, I now also don't have press. 0.038 divided by 100 times 17 plus 0.200 divided by 100 times 18. So you should get 16.00438. Round to 3 significant figure, you get 16.0. Okay? So now you understand why your mass of oxygen is 16. Okay, because it's 16.00438. No one's going to write the count number to do your calculation. Okay, so this is how you calculate relative atomic mass based on its abundance. Now, I just want to share with you that sometimes the question can be set a little bit trickier. So I just need you to just take note of this. They can be set a little bit trickier. What do I mean? Actually, what I can do is example this question. I could modify it. How to modify it to make it slightly trickier and tougher for you? I can say oxygen exists as oxygen 16, 17, and 18. I say oxygen has 99.762% of oxygen 16 and 0.038% of oxygen 17. Then this whole part here that I'm going to highlight in red, I delete it off. Okay, I delete it off. So I only just tell you the percentages of oxygen 16 and oxygen 17. I don't tell you about oxygen 18 at all. I don't tell you. So what you need to do is you need to take 100% minus the 99.762 minus the 0.038 to go and find out how much oxygen 18 there is. So don't always assume that we'll give you all the percentages adding up to 100. Okay, we can actually be a bit cheeky and give you something that doesn't add up to 100 because we expect you to calculate the next part to it. So that's where the questions are a bit trickier and cheekier. So just have to take note of that. Okay, let's go on. Okay, let's go on to the next part here. So those are relative atomic mass. Okay, so we're looking at atoms. But most substances don't exist as atoms. They actually exist as simple molecules. So many substances exist as simple molecules. Okay, simple molecules. So simple molecules generally when you have covalent bonding, or they can exist as your ionic compounds, which then you will use ionic bonding. Okay, so how to calculate the mass of these substances? Take note, the terminology we use is different, but the chemical symbol, but the symbol to represent it is similar. So mass of simple molecules is calculated as relative molecular mass. We call it MR. For ionic compounds, to find the mass of ionic compounds, okay, we actually calculate it as what we call the relative formular mass, but the symbol it is still also MR. Okay, so instead of writing relative molecular mass, relative formular mass, generally you can just write MR, okay, to keep it simple. So question, what the crap is relative molecular mass? How come I got another definition I must remember again? Okay, so this one, take note. Relative molecular mass of a what substance? Because it's a relative molecular mass, right? So this is what kind of a substance? Of a molecular substance. Okay, is the average mass of one molecule compared to what? Because it's relative molecular mass, right? So I want to find the mass of I want to find the average mass of one molecule of the substance compared to what thing? Compared to same thing, 1/12, okay, of the mass of a carbon 12 atom. Now, at this particular stage, you will be wondering, why is it still 1/12 of the mass of a carbon 12? Why is it carbon used as a reference? Why is carbon used as a reference? Because carbon 12 is actually one of the most abundant, okay, abundant, I hope I'm spelling correctly, abundant element, okay, / atom found on Earth. So it's the easiest to go and find and make reference to. That's why we compare it always to 1/12 of the mass of a carbon 12 atom. Carbon 12 is one of the easiest to find on Earth. It's the most abundant one of the most abundant element on Earth. Okay, so that's the reason why we actually refer to the carbon 12 as a reference point, why everything is referred relative to it. So relative molecular mass is the mass of, relative molecular mass of a molecular substance is the average mass of one molecule. So we're actually looking at the average mass of one molecule compared to 1/12 of the mass of a carbon atom. Okay, so then the question now is, how can I calculate the relative mass and relative formula mass of a substance? How to find? Okay, how to find? Very simple. I will show you an example first. So let's say, for example, I want to find the mass of HCl. HCl is a molecule. Okay, so this is a molecule. HCl molecule. I want to find the mass of HCl molecule. So question is, HCl molecule is made out of what? This guy here is made out of one H and one Cl. So to find the mass of one molecule of HCl, what I'm going to do is to find the relative, okay, let's use the symbol MR. To find the MR of HCl, I'm going to take the mass of one H plus the mass of one Cl. I'm going to take the relative atomic mass of one H and the relative mass of one Cl and add them up. So let's go back to our periodic table. H, the relative hydrogen relative atomic mass is 1. chlorine relative atomic mass is 35.5. So 1 multiplied by the relative mass of hydrogen, relative atomic mass of hydrogen, which is 1. 1 multiplied by the relative atomic mass of chlorine, which is 35.5. I'm going to get 36.5. So that's actually how you calculate the MR of your molecule, how to find the relative molecular mass. Okay, so I've shown you the working. So the question is how to write it down. How can I calculate it? So what does it mean in words? So what we are doing, it is calculated. Okay, it is actually calculated by adding together the relative atomic mass of all the atoms in its chemical formula. Okay. So this is how you go about, okay, calculating, explaining how you go about calculating the relative molecular mass. So I got a whole list of things here. So I'm just gonna go through, I'm just gonna show you maybe part 1 and part 4. Okay, I'm gonna show you MR of N2. So how to find the MR of N2? This is actually 2 times of N because I got 2N, right? Okay, so maybe don't need bracket. So the MR of N2 actually is to find the mass of 2 nitrogen. This is equals to 2 multiplied by, let's look at the mass. Nitrogen, the mass is 14. So find the bigger number, 14. So relative atomic mass of nitrogen is 14 over here. I'm going to get is 28. So this is the relative molecular mass of nitrogen, the MR of nitrogen. I'm going to show you something that's a little bit more difficult. Okay, I'm going to ask you all to go and do 5 on your own. I'm going to try question 4 to show you. So the MR of CaSO4 consisting of, this will actually be equivalent to 1 calcium plus 1 sulfur plus 4 oxygen. That's actually how you go about, that's number of atoms in the formula, right? Then, so calcium is actually, if you look at a periodic table, it's actually 40. For sulfur, it's actually 32. So it's good you can remember, it makes life easier for you. Then after that, for oxygen, it's actually 16. Okay, so if you were to take all this to add up together, you will actually get 136. Okay, so I want you to take maybe the next about maybe 3-4 minutes. I may give you now till about 5 minutes until 11:10. You can take a short break again. At 11:10, we'll resume. I'll go through the rest of the things again. Okay, so those of you who need some time to copy down some of the things, okay, I'm going to push it up a little bit more. Okay, so you can take the next 5 minutes to copy whatever you haven't copied yet and finish up the part 2, part 3, and part 5. Okay, so I'm going to pause the recording. Let's carry on. Okay, so periodic table, make sure you have it because when you're doing the mole, okay, a lot of you will need to refer to a periodic table quite a fair bit. Okay, let's go back to class cake. This worksheet now. Okay, so how to calculate the MR of the following substance? So for CO2, most of you would have calculated already. To find the MR of CO2, is actually taking 1 carbon plus my 2 oxygen. This will be equivalent to 1 times 12 plus 2 times 16. Okay, 32 plus 12, you're going to get 44. So CO2, the mass you calculated, the MR should be 44. SiCl4. So to find the MR of SiCl4, okay, so if you already follow the step, you shouldn't go too wrong. It's actually 1 Si plus 4 Cl. So Si is actually 28. Cl is actually 35.5. So if you were to take 28 plus 4 times 35.5, you're going to get 170. Last one, I think 5 is the one that some of you really find it quite challenging. So instead of straight away zooming in and just write all the thing, actually what you can do is try to expand the bracket a little bit. So this guy here actually tells you that there's 2 Fe and there's actually 3 SO4. 3SO4 tells me that I will have 3 sulfur and 12 oxygen. Okay, so I say again, Fe2SO4, 3 over here, tells me that actually there's 2 iron, so 2 Fe. SO4 bracket 3 over here actually tells me that I got 3 sulfates, 3 SO4. So 3 times of this means that I actually got 3 sulfur and 12 oxygen. So Mr of Fe2SO4 bracket 3, this is actually iron 3 sulfate. You're going to have 2 Fe plus 3 sulfur plus 12 oxygen. Okay, sorry, this looks like 120. Let me erase again. This is actually 12 oxygen. What you're going to get is 2 times 56. Okay, please let me know if I'm wrong. I'm just trying to remember based on memory. Okay, 3 times of 32 plus 12 times of 16. Okay, iron wrong should be 56. So 3 times 32 plus 12 times 16. So you're going to get 400. So it is possible for your relative molecular mass to reach 400. Okay, now some of you are thinking, how big can the mass go? Okay, now all the elements you're using now, you realize they're relatively getting heavier and heavier, right? Iron already 56. You can look at a periodic table, actually for copper, it's actually 64. Zinc is 65. Now, one of the heaviest elements that you actually see and possibly use would actually be lead. You realize lead is at the bottom here. But here you can see element number 82. Lead actually has a mass of 207. Okay, so don't be surprised if you need to use the number 207 for relative atomic mass. It's actually correct. It's for lead. Okay, so this is actually for the MR that we have calculated until end of worksheet 1. So let's go back to the first page. What have we done so far? What we have done so far, actually, we have learned to define relative atomic mass. So put a tick here if you think you can. Next, we have actually learned to explain why AR values, relative atomic mass, are not always whole number. We have explained that. We have actually calculated, okay, the relative atomic mass of elements based on the relative percentage of their isotopes. Now, these two, we actually did it as a package, right? In the explanation part, I actually did the calculation first, then actually went on to do the explanation. Next, we have actually gone to actually learn to define what relative molecular mass is, okay, and differentiate between relative molecular and relative formular mass. This guy here is for the covalent molecules. Okay, relative formular mass is actually for your ionic compounds. So that's how you actually differentiate between relative molecular mass and relative formular mass. But we kept it simple. We just use the symbol MR, okay, to go and say for both of them. Then we also learn how to calculate the MR of all the various compounds and stuff. So we have done this as well. So these 6 objectives are the things that we have actually done, and you should be able to do it, okay, after going through these worksheets. Okay, so worksheet 1 actually deals a lot with the basics of how to calculate what we call the relative atomic mass, relative molecular mass, and relative formular mass. In short, AR and MR. Okay, so right now it's 11:13. I will just push through to the next worksheet. We're going to cover a little bit more. Okay, so in the next worksheet here, worksheet 2, okay, I'm just going to cover 2 parts. I think actually quite a simple one. Okay, now, so we're going to go on to this concept of what is a mole. Okay, so we're going to cover this too. We're going to state the number of particles contained in 1 mole of a substance. We're going to be able to understand what is 1 mole through this worksheet. Second thing, we're going to learn how to calculate the number of particles, okay, when given the number of moles. Now, just want to highlight for these 2 over here, okay, the numbers can be very daunting. The numbers can look very scary, okay, but think of it like it's like a unit, okay, like 1 dozen is equals to 12. 1 mole actually means a certain number. So let's go on and start the thing. Okay, so let's look at the first part. Okay, so this, if you want to refer to a textbook, this is actually found on page 140 to page 141 of the textbook, okay, for my pure science students. So in 12 grams of carbon, so let's start, 12 grams of carbon, there's actually approximately this long string of numbers, which is actually 6 times 10 power 23 carbon atoms. So 12 grams of actually is equals to 6 times 10 power 23 carbon atoms. Okay, 12 grams of carbon actually consists of 6 times 10 power 23 carbon atoms. It's actually quite ridiculous number, right? It's so difficult. Once again, you know, they are just too big a number. Like relative atomic mass is so small, it's very hard to use that kind of mass, right? And hence, that's why I use relative atomic mass. So same thing, in terms of counting the number of particles, now the number of particles are just too many. To 12 grams, can you imagine 12 grams of carbon actually contain this big, ridiculous number of carbon atoms? It's going to be very difficult for the chemist to actually count them all to go and perform our calculation. So what we try to do is, we're going to use a mole, okay? The idea of a unit as a mole, okay? So 1 mole, okay? Take note, it's not the mole on your hand, the mole on people's face. It's actually, mole is actually a unit, okay? 1 mole. So we're going to use the idea of mole to calculate particles. Okay, so again, we're going to use the idea of mole to calculate particles. So the question is, in 1a, how many particles are there in 1 mole of substance? How many particles are there in 1 mole of substance? So we know that whenever we say 1 dozen, when we say 1 dozen, we know that it's referring to 12, the number 12. So when we say 1 mole, what is this number that we're representing? So actually 1 mole is actually representing 6 times 10 to the power 23 particles. So how many particles are there in 1 mole of substance? Answer is 6 times 10 to the power 23 particles. And what is 6 times 10 to the power 23? It's actually this long string of number over here. Okay, obviously we're not gonna be using this kind of numbers all the time. That's why, as I mentioned, we always use back 1 mole. Okay, so let's look at 1b. How many carbon atoms are there in 2 moles of carbon? Okay, this is not supposed to be like that. This is supposed to be bracket C, carbon, capital C, right? Carbon. So how many carbon atoms are there? How to calculate? Actually, very simple. Number of carbon atoms. Okay, what I know is 2 mole of carbon atoms, right? So I know it's 2. I know 1 mole is equals to 6 times about 23 particles. In this case, 1 mole is 6 times 10 to the power 23 atoms, right? So for 2 mole, it's actually 2 times 6 times 10 to the power 23. 2 mole. So actually this thing here is mole. So we can see 2 mole. So instead of writing the word mole, I write 6 times 10 to the power 23. So therefore, my final answer will actually be 12 times 10 to the power 23 particles. Now, because you're writing in standard form, sometimes you will realize that people will not write 12. Instead, they'll write 1.2 times 10 to the power 24. Okay, let me rewrite this. 1.2 times 10 to the power 24. Okay, atoms. Sorry, this is not only particles, this will be atoms. Okay. Can? So take note, that's why this is where this chapter you'll see a bit of math coming in. But safest is to just press a calculator. Cannot go wrong. Okay, just press a calculator. Unless you press calculator wrongly, then that one I also cannot save you. Okay, so 1A, 1B, I think generally we have explored the idea really in terms of what it means in terms of the quantity of 1 mole. So let's go on. How many oxygen molecules are there in 3 mole of oxygen gas? So number of oxygen molecules. Okay, I want to know how many molecules are there, right? So if I say that there's 3 mole of oxygen molecules, you can see oxygen gas actually O2. It's actually oxygen. If there are 3 moles of oxygen molecules, 3 moles. Okay. So how many oxygen molecules are actually there? How many exact number? It's actually 3 times 6 times 10 to the power 23. Because I'm asking you how many oxygen molecules are there, right? So therefore 3 times this number here, you're going to get 1.8 times 10 to the power 24 molecules. So I think right now, based on this, you realize that the word particle can actually means atom. The word particle can actually also mean molecules, okay, based on the examples we have done so far. Okay, so we are done 1A, 1B, 1C. 1A is to tell you 1 mole got how many particles. 1B is ready to go about calculating what exactly 2 mole means. Part C is to calculate 3 moles. Okay, what exactly does it mean? So I know that there is 1.8 times 10 to the power 24 molecules of O2 in 3 moles of oxygen gas. So I repeat again, listen carefully. There is actually 1.8 times 10 to the power 24 molecules of O2 in 3 moles of oxygen gas. Okay. This is the number of molecules of O2. Now, part D. I want you to look at part C and then look at part D. So the question is, what is the difference between part C and part D? What is the difference between my part C and my part D? Okay, so this is the thing I need you to take note. What's the difference between part C and part D? Is actually the word here. This is actually molecule. This is actually atom. Okay, so what's the difference, right? Now, ask yourself. 1 oxygen molecule will give me how many oxygen atom? Oxygen molecule is O2. Oxygen atom is O. So 1 oxygen molecule will give me how many oxygen atom? The answer here is 2. Okay, so I repeat again. 1 oxygen molecule gives me how many oxygen atom? Because I know oxygen molecule is O2. Okay, so 1 oxygen molecule will actually give me 2 oxygen atoms. Okay, 2 oxygen atoms. So now I know that actually in 3 moles of oxygen gas, there's actually 1.8 times 10 to the power 24 molecules of O2, right? So how many atoms are there? So what I'm going to do is 3 mole of O2 is actually equivalent to 1.8 times 10 to the power 24 molecules of O2. So you realize your statements become very important. Huh? So 3 moles of O2 actually is equivalent to 1.8 times 10 to the power 24 molecules of O2. So 3 mole convert to the particles of molecules. This is equivalent to how many atoms of O? So you realize from here to here, okay, from my second part to my third part, here to here, is very similar to what I've done here. I'm just going to multiply by 2. So this is about understanding logic. Okay, so this is where you'll know that, okay, because O2 convert to O. So which means that if I take this number multiplied by 2, I'm going to get 3.6 times 10 to the power 24. I think some of you are getting quite scared because numbers look so scary. Wow, this 10 to the power 24 kind of thing. Okay, don't be scared of numbers because you always have your calculator to crunch it for you. Okay, most important thing is understand the concept behind it. How you convert from mole to the particles. Okay, and then try to differentiate the finer details in terms of a molecule and an atom. This is where you realize your chapter of your element, compound, mixture comes into play. So your chapter 4 may seem very easy, relatively harmless, but that's where you realize that, oh, okay, quite important. You don't know how the atom molecules actually makes a difference, then GG. Okay. So I'm gonna do the last one. Okay, how many hydrogen ions are there? Instead of maybe instead of me doing, let y'all do. I want y'all to start with this first. Okay, start with this first. Instead of straight away going to hydrogen ions, I want you to do a part 1 first. Part 1 is to ask how many particles of H2SO4 are there in 5 mole? So first is to find how many H2SO4 are there. Okay, how many particles actually is particles may not be such a best word to use, but how many H2SO4 are there in 5 mole? That's the part 1. Only when you're done with part 1, you know how many H2SO4 are there. Then I want you to go and try part 2, which is how many hydrogen ions are there in 5 mole of H2SO4. So I break it down for you already. First, find out for me how many H2SO4 are there in 5 mole. After that, then you go into how many hydrogen ions are there. Okay, so go and try E part 1, try E part 2 now. Okay, maybe I'll give you about 2 to 3 minutes to go and figure it out. After that, at 11:28, I'll go through the answer. Okay, so please carry on. I'm gonna pause the thing now. Wait. Sorry, my thing jam again. Oh no. Okay, never mind. Now I'm gonna do a bit of a silent treatment here because I realize I can't. My thing is not really shifting properly. Okay, let me try to pause my recording. Okay, let's resume the recording and let's go through the answers here. So how many particles of H2SO4 are there in 5 mole of it? So first thing, let's find number of H2SO4 particles. Because the idea is 5 mole, right? So this is actually 5 multiplied by 6 times 10 to the power 23. So you realize the word mole, you can actually just replace the word mole with this number 6 times 10 to the power 23. You do your math, you're going to get 30 multiplied by 10 to the power 23. This is actually equals to 3.0 times 10 to the power 24 particles. Okay, to be more precise, H2SO4 particles are. I'm going to write H2SO4 at the top here, particles. Okay, so this is what you have done for part 1. Then now it's about making sense. Okay, now it's about making sense. So if you go to your thinking about how many hydrogen ions are there. So what I know is H2SO4, if I were to put it in water and let it dissolve, this is actually my sulfuric acid. For 1 H2SO4, I'm going to get, I say again, for 1 H2SO4, I am going to get 2 H plus, and I'm going to get 1 SO4, 2 minus. So what I know is 1 H2SO4, this is going to produce, okay, this is going to have 2 H plus ions when I dissolve it in water. Okay, so ions are actually particles. So we are looking at the particle now. So I know that 5 mole of H2SO4 means that I'm going to have 3.0 times 10 to the power 24 H2SO4 particles. Then this is actually equivalent to how many H plus ions. So like what you have seen here, okay, H2SO4 to H plus actually is a 2 times, right? So same thing from here to here is actually to multiply by 2. So your final answer will actually be 6.0 times 10 to the power 24 H plus ions. Okay? 6.0 times 10 to the power 24 H plus ions. Okay, so this is the end of worksheet 2. Okay, this is the end of worksheet 2, which is just nice 11:30. So what we have actually done here, so just to wrap it up, once again, let's go back to our success criteria and really see it. Okay, so what we have done is, are we able to state the number of particles containing 1 mole of substance? Yes, we have done this. What we mentioned was 1 mole actually is 6 times 10 to the power 23 number of particles. Okay, next, are we able to calculate number of atoms, molecules, or ions when given number of moles of substance? Okay, what we have done here, we've gone through examples of it. So yes, we have done the calculation. But the question is how confident you are when given something like this. So those of you who want a bit more practice, what you can do is, okay, you can come and find me to ask for the answers, but I'm just going to give you 2 additional questions here. Okay, I'm going to not break it down for you. You can find out on your own. So the first one would be, how many Cl minus ions are there in 3 mole of CuCl2? Okay, how many Cl ions are there in 3 moles of CuCl2? Okay, this one I tell you got 2 steps. So I'm going to write in blue here. I'm going to tell you that this one clear cut. There are actually 2 steps to it. Got to do a part 1, got to do a part 2. Okay, otherwise you're going to get issues. So same thing, I'm going to give you something similar to it. So if you're able to do it, it's good. Next is how many, Heather, what is how many? Let me give you an interesting one. How many oxygen atoms are there in 4 mole of SO3 gas? So this one, once again, this is going to be 2 steps also. 2 steps. Okay, so write down these questions. Okay, write down these questions. Okay, write down these questions. Yeah, okay, write down these questions. I will not be putting this up, I'll upload the video. Okay, I'll upload the video onto YouTube, and then you can actually be looking at it and then write down the question itself. Okay, so for the next session, I will not, I use the word, I will not, okay, go through this. I'll just straight away start the next worksheet. So for those of you who want to do and find out what the answer is, you can come and find me. Okay, I will let you know whether your answer is correct or wrong. Okay, so that's all for today. As I mentioned, we'll end by 11:30. I'm a bit over time, but I guess that's all right. Only 4 minutes only, yeah? Okay, so let me stop the recording here.